Today I'm going to talk about the multi-gate transistor, so like a FinFET or nanowire FET. And before talking about this multi-gate, we should know about the MOSFET scaling. We wanted to make decrease the area, so make lots of transistor in one wafer, or decrease by the decreasing of gate length, and we wanted to increase the drive current, but under the 130 nanometer node, there was a problem, like by the device scaling down, the subthreshold swing becoming very poor, so and by the device scaling down, um we wanted to scale up the drive current, but it increased, but the amount of increasing is become smaller. So there was like this problem, and because of this, we in the company they have a solution like a FinFET, and this FinFET is a uh, very thin channel that is controlled by the three side of by the gate, like side of two place and the top. So, but in first they tried about the SOI FinFET, and there was a problem of two things, and this two thing is like the wafer is very expensive, and the other problem is like SOI thin films uniformity. And by this problem of the solution was a GAA FET or nanowire FET. First, in nanowire FET is have a very thin channel, like a thin SI channel, so but this in SI channel makes lots of problem like a defect or series resistance, and the process control is difficult. Um, like this problem, and before this one in the planar structure, there was a double gate MOSFET, but this double gate MOSFET have a problem like the making the backgate in the SOI wafer was very difficult, and making the align of the top gate and back gate was very, very difficult. So it doesn't be common um in the MOSFET, and the it became to the like FinFET or nanowire FET. And before knowing this, we should know the fully depleted. It is like um this fully depleted is like the MOSFET is off, but already channel is channel is all depleted by the gate 1 and gate 2, and it makes threshold voltage higher, so it can be the impurity of the VT roll off. And um, and then I will talk about the FinFET, but this FinFET is before this FinFET, the planar MOSFET is determ the planar MOSFET's drive current determined by the width and the length. But in the FinFET, there is the fins. When we control the fin height and the fin number, we can control the drive current very easily. So it is better gate. It have a better gate i- control better gate controller than the planar MOSFET. And when we use the FinFET that the fin is already fully depleted, we can make the N like similar to the one. So, and this means the swing value become the like minimum. So 60 millivolt per decade. So this means the FinFET is good. And mm, mm, and then I want to talk about the quantum mechanical effect, and this is like mm, when the SI layer is under the 10 nanometer, the when the SI thickness become smaller, the threshold voltage become smaller together, but when thickness of Si is smaller than the 10 nanometer, by the quantum mechanism effect, the threshold voltage becoming increase. And in the silicon film thickness is like 10 nanometer, the mobility is the biggest biggest. And when the silicon film thickness become more thin than the 10 nanometer, the volume inversion, it becomes volume inversion, but the carrier is very close in the surface, so it have a effect of the surface of roughness scattering, so the mobility become decreasing. And it is, I think it is all of my video. Thank you.